Good morning, everybody. So, today we're going to talk about problems involving ropes and pulleys. All right. A key assumption to make in these problems is that, well, we'll find out. But yeah, all right, let's go. All right. So here are key assumptions to make for these problems. All ropes and strings will be massless. All right. All ropes and strings will be massless. Okay. So what does that help us unlock? How about we try and see by analyzing this system of a boy pulling a box through a rope. All right. And we're going to analyze the rope itself. I'm going to analyze the box. Okay. So what does the rope feel? The rope feels the pushing force from the boy. All right. What does the rope feel? Well, the rope feels the force of the box on the rope. All right. Now, what does the box feel? The box feels a tension from the rope pointing towards the person, and then really it also feels the box is on the surface, so it feels the normal force and our weight. Okay, so upper body diagrams. Let's analyze the dynamics. Let's look at for the rope. Let's look what's the next direction for the rope. So rope X direction. F push. F box on rope. Alright. So F push is in the negative direction. F box on rope is in the positive direction. I really wish I had arranged them better, but apologies. And then for our box, really we have. So I'm ignoring the y direction because they will cancel out. And the rope is not on the surface. I'm saying the rope is massless. All right. So the rope doesn't have a weight or a normal force. All right. The rope is massless, so W equals mg. M is going to be 0. So the gravitational force is the gravitational pull on the rope is 0 because M is 0. All right. Hope that's clear. So let's see. Rope has no weight because it is massless. All right, just remember that. Now, box. Again, so we have in the y direction we got Fy equals normal minus weight. In the x direction, we only got tension. All right, so now let's look at let's only analyze the y direction here. All right. Remember, we said the rope is massless. So if we're looking for, let's see, yeah, I'm just going to lower down. Say the rope is massless over here. So I'm looking at the rope again. So when we apply our Newton 2 condition for the rope, max is going to be equal to F push plus F of box on rope. Our rope is massless, so M is 0. So we're kind of in an equilibrium here. Yeah? So if I just rewrite that over there, box on rope. All right. Then I take my F push across. I see my F push is equal to the force of the box on rope. Wait, so okay. Now what's the magnitude of the box on the rope? Well, this is a third law force. Now, box on the rope and tension, whilst my R's are not equal, I apologize for that. They should be equal. But the box on the rope and the tension right here in my drawing are forming a third law pairing. Alright? So my tension is felt over there. It's going to be acted on by the box, and so it's acted by the box on the rope, and the rope is also acting on the box. Alright? The rope, so F of box on rope, we also have a tension right there. So really, if my strings are massless, my box on the rope will always be equal to my tension. Alright? This is what this is telling me. Alright? Okay, so it makes why does dealing with a massless spring make our math easier? Well, that's because the tension in a massless spring or rope equals the magnitude of force pulling on the other end of the rope. You see? So our tension is equal to the force box on the rope through here in this case in particular we have a Newton 3 working here. Alright? So and that's how we're able to see that relationship through Newton's third law. Okay. So yeah. Through Newton 3. Okay. So let's talk about pulleys. Alright. A pulley is a wheel that redirects tension in a rope to lift or move objects. Alright? So this is here's just a drawing of a pulley. Yeah. Most of the time in AP, we'll be talking about an ideal pulley. Alright? So, what is an ideal pulley? Well, I would say an ideal pulley is one that is massless. Alright? It's massless. Number 2, no friction is experienced by the pulley when a rope goes over it. Alright? So like here in this case here, we have no friction because we're dealing with an ideal pulley. Most of the time we'll always be dealing with an ideal pulley, unless explicitly stated otherwise. So yeah. So because friction is not because we're ignoring friction on the pulley, the tension, all right, just try to remember this statement. The tension, so because we're ignoring friction in the pulley, that's right, and our string is also massless. So because Apologies. Let me reset. Okay. So, just a major point right here. Major point. Alright? So, because the strings we will be dealing with, so this is strings, ropes as well, are massless. Yeah? And what else? The pulleys are massless and frictionless. This probably can be written grammatically a little bit better. All right. The tension in a massless string will be unchanged. Or remain unchanged. I think remain is a better word. When it goes through a pulley, when it goes over a pulley. All right. So, okay. So, just one more recap. A little bit more recap before we dive into solving problems. Okay, so yeah. So things to remember when working with massless ropes and strings. All right. If a force pulls on one end of the spring. Oh, sorry. One end of the rope. The tension will equal the magnitude. That's the tension in the rope, yeah? Equal the magnitude of the pulling force, as we just saw earlier. This is it. So as we saw earlier, it's okay. So, what else to remember? If two objects are connected by a rope / string, which is the same thing, the tension will be the same at both sides. All right, so if I have something like this, I have my massless string, M1, M2, tension is the same at both sides, because I have, so yeah. This is what we mean by two objects connected by a rope or string. And then, last point, if the rope passes over a pulley, the tension is unaffected. The tension in the rope remains unaffected. Okay, so let's study. Let's do some fun problems. Yeah. Let's look at our artwood machine. Yeah. Nice. Okay. So free body diagram, coordinate system. Let's see, for M1, I have a different color for M1 and M2. So let's see. I have two masses here connected over a pulley. Alright? So free body diagram, we need two different masses for two different free body diagrams for M1 and M2. You're only experiencing forces in the y direction, nothing in the x. So we have here we have for M1 we have a tension going up, and then we also have the weight going down. That's M1. And M2 is really the same. M2 we got a weight, and we also got a tension. Alright? Awesome. So remember our law here, the law that we, this law over here that we, not really the law, but the principle to remember. These two over here. If two objects are connected by a rope or string, the tension will be the same at both sides. Alright? If the rope passes over a pulley, the tension in the rope is unaffected. So because of that principle, when analyzing our forces in the y direction for both of them, it's M1. Oh my god. This is M2. So if I say force in the y direction, I have, so this is for M1. I'm going to have T minus the weight. And then there, same thing, M2. So T minus weight 1 because of M1. Same tension minus, minus weight. Weight. Alright? And that's what we have. Okay, let's plug in our magnitudes for weight. So we're gonna have M(A1) it's going to be equal to T minus M1G. Alright, same thing for here. So this is going to, I'm going to just give you a little title here, mass 1 and mass 2. It's going to be MA2 to be equal to tension minus M2G. Alright, so now what can I do here? So what do we want to know? What do we want to know? Alright, what do we want to know? So we want to find out the acceleration of the masses. Alright, the acceleration that the pulley is going to undergo. Alright, we want to know the acceleration the pulley will undergo. Alright, there's one more principle that we can use here that we've used in the past. Alright, because I'm connected over a pulley, my acceleration, so A1 is going to be equal to A2. And you can think about it as, because they're also in contact, so the acceleration is the same, but that's a very sketchy way to think about it, which can lead you into various traps in other questions. But because I want you to think about this in this way. We're connected over a pulley, so our acceleration is the same. So we're gonna, if we have MA, so M1, apologies, M1 A is going to be equal to our tension equal M1 minus G. For mass 2, the same thing. M2 is going to be equal to A tension. All right. I think you can see where this is going here. A is the same, so I can do some algebra right here to get the value of A. So I have a system of equations. I'm going to write them both here. All right? I'm going to write them both right here. M1 A is equal to tension. You see, this is our system of equations. Is equal to tension minus M1G, and M2A is equal to tension minus M2G. All right, this is our equation 1, this is our equation 2. Okay, so we can solve for, so what we want to know is A. So you can't really be solving for A because we're going to lose it. So let's find that, let's solve for tension because the tensions are the same, and then plug it into one equation. All right, so if let's say I manipulate equation 2, I'll say my tension is going to be equal to M2A plus M2G. Yeah? Which is really equal to, T is going to be equal to M2, all right? You have in brackets A plus G. Yeah? Yeah. And by the way, we have directions of acceleration. So M1 accelerates up and M2 accelerates downwards. So this acceleration is negative. So this truly is a negative acceleration, but we'll fix that later. All right, so let's plug this into M1 for our tension. Into equation 1 for our tension. So plug into equation 1. Then we're gonna have M1A equal to, let me just put a little line there for clarity. That disturbs me. Okay. It's equal to M2A plus G minus M1. All right, I plugged in for the tension. Okay, what we can do now here is try to have everything on the same side, because now we just have a messy algebraic error, algebraic mistake. So I'm gonna put the minus sign for M2 just right there, so we don't lose it by mistake. Okay, now the physics mistake is almost done. Really, I just need to move my accelerations on one side, have my masses and G on the other side. All right, so I forgot my G over here. So I'm going to move, let's just manipulate this. I'm going to move this guy across. A minus M2 minus A plus G is going to be equal to minus M1G. All right, I'm going to expand my guy in parentheses, M1 minus M2A plus M2G is going to be equal to minus M1G. All right, and then from here I can just get my A out here, and I got M1, hold on, it's going to be plus because of the minus sign, M1 plus M2 is going to be equal to, no, not yet, not just yet, plus M2G. Is it a plus M2G here? Yes, it is plus M2G. It's going to be equal to it's going to be equal to minus m1g. All right, so I'm getting there. So I keep my a on this side. It's going to be equal to minus m1g plus m2g. All right, so then now you see I've just moved this guy across. I get my a, I can factor out my g here, say m2 minus m1, factoring out my g over there. And then I can divide the whole equation by m1 plus m2. M1 plus m2. All right, and there's your example. I had more examples, but I'm only going to give you one example because I don't want this video to be like 50 minutes. All right, so this problem shows you how we should treat tension when we have a rope, how we should treat accelerations. You know, a lot of things here are the same. So really, you know, it's you're really treating everything as the same almost, you know. So yeah, I hope you get the chance to watch this video. All right, and by the way, let me just be careful with my statement. Here in this case, the tension is the same magnitude and the acceleration is the same magnitude. So that allows us to create a system of equations to solve for our needed value. All right, so you need some algebra 2 skills a little bit. And don't worry, we'll have a lot of practice with these things. Anyway, have a good day, guys. I hope you enjoyed this video. Bye.